Now, what is electrochemistry? So, electrochemistry constitutes one of the most important interfaces between chemistry and everyday life. So, every time you start a car, turn on your calculator, use your smartphone, or you listen to a radio at the beach, you are dependent on electrochemical reactions. So, we can say our society sometimes seems to run almost entirely on batteries. In addition, we can also say many important industrial materials such as aluminium, chlorine, sodium hydroxide are prepared by electrolytic processes. Now, another aspect of electrochemistry is in analytical chemistry, electrochemical techniques use electrodes that are very specific for sensing or recognizing molecule or ion. Now, for example, we can say proton. For that, we have pH meters, we have dedicated electrodes for sensing fluorine or fluoride, okay, chlorine or chloride, okay, and many other toxic metal ions, okay. So, these increasingly important methods are used to analyze trace pollutants in natural waters that can affect the aquatic system, or for tiny quantities of chemicals inside human blood, okay, that may signal the development of a very dangerous disease, okay, and we can identify such diseases at a very early stage by using electrochemical techniques. Electrochemistry is best defined as the study of interchange of chemical and electrical energy. Now, what is oxidation states? Rather, what are oxidation states and oxidation reduction reactions? Now, we determine whether a given chemical reaction is an oxidation reduction reaction by keeping a track of oxidation numbers, also known as oxidation states, of the elements involved in the reaction. Now, here we have metallic zinc reacting with an acid, okay. Let's consider this is dilute acid, dilute H2SO4. Now, H2SO4 is a dry protein, so we're using two such protons, and it leads to the formation of zinc equated ions and liberation of HCl. So, this is laboratory preparation of H2, okay, basically. Now, this is a redox reaction, or we can call it as oxidation reduction reaction. So, how do we determine that? Now, we have studied before when we have studied the rules for finding out oxidation numbers of elements, or we can say anions or cations. So, when zinc is in its elemental state, it will be having 0 oxidation state, and proton is having +1 oxidation state, whereas zinc over here is having +2 oxidation state as a zinc ion, and hydrogen in its elemental state is having 0 oxidation state. So, what can we say? Let me write the oxidation states over here. So, this is 0, +1, +2, and for H2 it is 0. So, zinc, when it goes to zinc 2 plus, it has lost 2 electrons, okay. And when proton goes to H2, it has gained 2 electrons, okay. So, over here the one that has lost electron will be called as a reducing agent or a reductant, and the one that has gained electron will be called an oxidizing agent or an oxidant, okay. So, in a sentence we can say that substances or substance that oxidizes another substance, okay, that is proton oxidizing zinc, is called either an oxidizing agent or a oxidant. Now, in the process, the oxidizing agent acquires electrons from other substance That is, proton is taking the 2 electrons from the zinc and itself it is getting now reduced. Okay. What about the reducing agent? If you have to define it in a sentence, we will say is a substance that gives up electrons. So the zinc is now giving up electrons, thereby causing reduction of another substance, that is the reduction of proton over here. So the reducing agent is therefore now, after losing the electron, getting oxidized in the process. Okay. So now we will be identifying oxidizing and reducing agents. In illustration 1, what is the reducing agent in the following reaction? So we have been given the reactants Br minus reacting with hydrogen peroxide in an acidic medium, and the products are bromine and water. So to find out which one is the reducing agent, what we will do is we will assign the ions and molecules their oxidation states. So bromide is -1, oxygen we will say in a peroxide is -1, proton is +1, Br2 is 0, and oxygen inside water is -2. So from here easily we can say that Br minus 2 such bromide, if it loses one electron each, it leads to the formation of Br2. Okay, and we will say, rather over here, 2 electrons are lost. So one that loses electron obviously is the reducing agent. So our answer over here is going to be Br minus. Okay. Now, balancing redox equations. So whenever we balance a chemical equation, we must obey law of conservation of mass. What does it mean? That the amount of each element must be the same on both sides of the equation. Atoms can neither be created nor destroyed in a chemical reaction. As we balance oxidation reduction reactions, there is an additional requirement, that is charge balance. So what does it mean? The gain and losses of electrons must be balanced if a substance loses a certain number of electrons during a reaction. Another substance must gain the same number of electrons. So now we can say that electrons, just like atoms, are neither created nor destroyed in a chemical reaction. What are half reactions? Now, reactions that show either oxidation or reduction alone are called half reactions. So we have been given one example over here, wherein we can see ceric is reacting with ferrous ion and forming cerium ion and ferric ion. So now let us decide, using again oxidation numbers, which one is undergoing oxidation and which one is undergoing reduction. So over here, cerium 4+ means the oxidation state is +4. Fe2+ means oxidation state is +2. Cerium 3+ means oxidation state is +3. And Fe3+ means oxidation state is +3. So we can see easily that ceric is undergoing reduction, rather 1 electron reduction. So that is why we will say reduction. Cerium 4+ equated plus 1 electron, giving you cerium 3+, okay, equated. Now for oxidation we will say Fe2+ equated arrow, giving you Fe3+, and there is a loss of electron. So whenever there is loss of electron, process is oxidation. Whenever there is a gain of electron, process is reduction. Now balancing equations by the method of half reactions, also known as the ion electron method. Now we will learn some rules, as in how to balance redox reactions in acidic aqueous solutions. So first of all, what we do is divide the equation into one oxidation half reaction and one reduction half reaction. Now we have to balance each of these half reactions. So how do we do that? First, balance elements other than hydrogen or oxygen. Next, balance oxygen by adding water as needed, and then we will balance hydrogen by adding proton as needed. Finally, we will balance the electrons, we will balance the charge by adding electrons as needed. Now, if at this stage, in both the reactions, the number of electrons are not same, then what do? We will multiply half reactions by integers as needed to make the number of electrons lost in oxidation half reaction equal to the number of electrons gained in the reduction half reaction. And then after this, we will add both the half reactions, and if possible, we will simplify the equation further by cancelling species that are appearing on both sides of the combined equation. And finally, while we think we have solved the problem, we will check and make sure that the atoms and the charges on both the sides are same. Okay, here now, balancing redox equation in acidic solution, we have been given illustration 2. Complete and balance this equation by the method of half reaction. So whatever we discussed in the previous slide is now given in this picture in a flow chart. Okay, so let us first assign these ions or molecules their oxidation numbers. Okay, so now for Cr2O7 2 minus, okay, let us recollect whatever we had learned in oxidation number in the chapter of reaction in aqueous solution, and there we had learned that to find oxidation numbers, okay, we assign the one we are going to find as x. So now there are 2 chromium, so it is going to be 2x, and oxygen is having -2. Now there are 7 such oxygens, so it is going to be multiplied by 7, and the algebraic equation that we are getting should be equal to -2 because the charge on this ion is -2. Okay, so that means that chromium in this is going to have +6 oxidation state. For chloride, it is very easy. We can simply say this is -1. Over here on the product side, chromium is having +3, and chlorine, because it is chlorine gas, elemental state, it is going to be 0. So now we have assigned the oxidation numbers for each of these molecules or ions given to us. So from here we can now tell that since it is going from a +6, that so the chromium we are saying that it is getting reduced, and chloride from -1 it is going to chlorine gas, so it is getting oxidized. Okay, so we say the reduction half equation is going to be Cr2O7 2 minus arrow Cr3 plus. Now the rules that we have studied, in that we had to balance atoms other than hydrogen and oxygen first. So here there are 2 chromium, so we will say Cr3 plus should be multiplied with 2. Now we have to balance oxygen, so we would write water, and that has to be now multiplied with 7. Okay, now we are having extra hydrogen on the left hand side, right hand side. So in the left hand side, we will balance the hydrogen by adding protons. So we will add 14 protons over here. And now we have to do charge balance because the atom balance has been done. So we know that chromium over here is +6 going to +3. There are 2 chromium. So for 2 chromium, the loss of electron is 6 electrons. So now we add 6 electrons in the left hand side of the equation. So let us now write the oxidation half equation, and we would write Cl minus going to Cl2 gas. There are 2 chlorine on the right hand side, so on the left hand side there should be 2 chloride, and now the loss of electron from each chloride is 1, leading to the formation of Cl2. So in total it is losing 2 electrons. Now in equation 1 and equation 2 we can see there is an imbalance of electrons, so we have to multiply equation 2 throughout with integer 3, and now we will combine these equations to get the final equation, and there we would write 14H plus aqueous plus Cr2O7 2 minus aqueous, electrons are going to get cancelled, plus 6Cl minus aqueous arrowhead. Okay, and then we would write 2Cr3 plus aqueous 7H2O and Cl2 gas. Okay, for H2O we write liquid. Okay, and this should be multiplied with 3. So let us now check if all are balanced. Hydrogen we have 7 multiplied with water, so we will say in total there are 14 here. So for that we have 14 protons over here. Okay, now there are 2 chromium, fine. How many oxygens? 7 oxygen on the right hand side, left hand side also 7 oxygen. How many Cl on the right hand side? 6. Here also we have 6. So the equation is now completely balanced. Okay. Another problem in which we have to complete and balance this equation by the method of half reaction. So just like before, again, let us first assign the oxidation states. So each oxygen is -2. There are 4 such oxygen, and we are taking the oxidation state of Mn as X. So the algebraic equation will be X plus -2 times 4 equal to -1. So Mn is having the oxidation number plus 7. We would say the oxidation state of carbon is over here X. Since there are 2, so we write 2X minus 2 times 4 equal to -2, and the value of oxidation number of carbon over here is going to be plus 3 as we solve this algebraic equation. Over here we take this to be as X. This is -2 times 2 equal to 0. So over here carbon is +4 oxidation state. What about Mn? This is in +2 oxidation state. Now having a look at the oxidation numbers, we can clearly say that for reduction half equation, we will say MnO4 minus going to Mn2 plus. We will balance the oxygen now because Mn is already balanced. So we would add water, and there should be 4 such water molecules. And now to balance the hydrogen, we would add 8 such protons. 7 is the oxidation state of Mn in the left hand side going to +2. So we can say that it is accepting 5 such electrons. What about oxidation? Half equation. In that we would say C2O4 2 minus, which is the oxalate ion, is going to CO2, and in the process it is losing electron. So it is losing, each carbon is losing one electron. Okay. First of all, we have to balance the carbons. So we will multiply with this with 2. So now the carbon and oxygen both are balanced. Now we will do the electron balance. Okay. So if it is in +3 and going to +4, two such carbon are going to +4 from +3 oxidation state. So obviously we will say there is a loss of 2 electrons. Now as we can see in both the equations, the number of electrons are not balanced. So what we would do, we will multiply first equation with 2. Better to write like this. And the second equation with 5. And then let us combine both the equations to get the final equation. So every time we write, we're going to multiply these integers with 2. Okay, so 16 H plus, and then we write equated because the reaction is taking place in acidic medium, plus 2 MnO4 minus equated. Electrons are going to get cancelled because there will be 10 in each equation after the multiplication. Then we write 2 Mn2 plus 8 H2O. So now we add this one. Okay, so we add plus okay, and nothing else. So now we can say that the equation is mass balanced and also charged balanced. Okay, let us go to the next slide. Okay, so in this slide we learn about balancing equations for reactions occurring in basic solution. How to balance redox reactions in basic solution? Now the rules are: balance the half reaction as if they were occurring in an acidic solution. Count the number of proton in each half reaction and then add same number of OH minus ions on each side of the arrow, okay, or the half reaction. So we'll ask question 4, complete and balance this equation for redox reaction that takes place in basic solution. So over here, this will be going to be a little big solution. So just we'll determine the oxidation states over here in this slide, and then we will do the solution in the next page. Okay. So Cn, what is the oxidation state of carbon over here? Okay. So if we say X is the oxidation state of Cn, then -3 is for nitrogen, and that is equal to -1. So for Cn, we will say it is +2. For MnO4 minus, if we take this one to be as X, and this will be -2 times 4, and then since it is MnO4 minus, so that minus is written over here. Okay. So now we will be saying that MnO4 is having the +7 oxidation state. What about here? So if you just draw the Lewis structure of the CNO, so as you can see, it is connected to N and O both. So this is -3, this is -2, and this is X. So we are having X minus 5 equal to -1, and that should mean the value of X would be +4. So we can say from here itself that Cn minus the C over here is getting oxidized to C +4. Okay, the oxidation state of C +4 is cyanate ion. Okay. What about Mn in MnO2? So this is X, that is 2 minus that is x minus 2 times 2 equals 0. So this is plus 4. And now we can say, having a look at both the oxidation states, we will say permanganate ion is getting reduced to manganese dioxide. Okay. So let's carry over this information, okay, into the next slide. So now for reduction half reaction, reduction half reaction, we will say it is MnO4 minus going to MnO2. So first of all, atom balance, because already Mn is balanced. So we will add water, and we have to add 2 water to balance the oxygen. So now to balance the hydrogen, we will add 4 proton. Okay. Now to balance the number of electrons, we will add 3 electrons over here. Okay, because 7 plus 4, the difference is 3. Okay. Now what about the oxidation half reaction? So that is you have to balance the oxygen, so we add water in this left hand side. Okay. And now if you have to balance the hydrogen, we will add 2 proton on the right hand side, and the number of electrons has to be added on the right hand side. Okay, so now this is a balanced equation, but the rule was after we add the protons, we have to add OH minus ions and then proceed. Okay, so again we will rewrite these equations by adding the OH minus ions. So 3 electron plus MnO4 minus plus 4H plus 4OH minus, and that gives us MnO2 plus 2H2O plus 4 4OH minus. So now in the next step we will be combining these two. Okay, so 3 electron MnO4 minus 4H2O MnO2 2H2O 4OH minus. Now within this step only we will cancel out the water molecules, okay, that are appearing on both the sides. So what do? We take out 4 from here, we write 2, and then we take out this water molecule from this equation. Now this becomes a completely balanced equation, and we can recheck this. Okay, 4 hydrogens, 4 hydrogen, all total 6 oxygen over here, here also 6 oxygen. Okay, so it is balanced so far. What about this? So for that we need to write Cn minus plus H2O plus 2OH minus, giving us CNO minus 2H plus plus 2OH, and just keep thinking that this is going to be 2 water molecules. So now we will erase this and write two water molecules, and again think that here there is 2 water molecule, there is 1 water molecule, so erase this one, and now write only 1 water molecule, and now again we have to recheck. So 2 oxygen, here also 2 oxygen, 2 hydrogen, 2 hydrogen, So now Cn, here is Cn, so these are balanced. Now this is the balance, say, equation 1, and this is, let us say, this is 2. Now the idea is that both the electrons should be balanced in the reduction half reaction and the oxidation half reaction for them to be combined to produce the final equation, So this entire equation needs to be multiplied with 2, and this entire equation needs to be multiplied by 3, and then we will add, So this is going to give us 6 electrons, so we will write 6 electrons, 2 MnO4 minus 4 water molecules, 2 MnO2, 8 OH minus ions, 3 Cn plus, we will say, 6 OH minus ions. On this side we are writing for these ones, so this will be plus 3 CNO minus 3 H2O, 6 electrons. Now to even simplify the reaction further, we will be cancelling out some common things. So 6 electrons removed from the equation. Here there is 8 OH minus ions, here there is 6, so we will remove this one, and we remove this and we write 2 over here. There are 4 water molecules, there are 3 water molecules over here, so we remove this one and we just write 1 water molecule over here, Now again, if we recheck, Cn, number of hydrogens, we are having 2, Number of oxygens, 3, 5, and over here we are having 4, so that is 9, and here too we are having 1, and then we are having 8 over here, so this is also 9. So now we can say that this is the final answer for the previous equation, in the previous slide. So the answer will be this one, This is the answer. Let's go to the next slide. Illustration 5. Complete and balance the following following oxidation reduction reaction in basic solution. So we have been given CrOH whole thrice plus ClO minus going to CrO4 2 minus, that is chromate, and producing Cl2, that is the gas. So now again we will assign the oxidation states to solve such a problem. So if this is taken to be as X, we know this is minus 3 equal to 0, so this is plus 3. This is taken to be as X, this is minus 2 equal to minus 1, so this is plus 1. This is taken to be as X, this is 2 minus 2 times 4 equals minus 2, so this is plus 6. And over here, this is 0 because it is in elemental state. So from here itself, we can say that plus 3 chromium is going to plus 6, so oxidation is taking place. And plus 1 Cl is going to 0, so reduction is taking place over here. So over here, we will say now oxidation half reaction or equation is CrOH whole thrice going to CrO4 2 minus. Okay. Now there is a chromium over here, it is balanced, okay, but there is an imbalance of oxygen and hydrogen, okay. So we have to think about that. Now let's go for the reduction half reaction, okay. So over here we will write ClO minus going to Cl2 plus. So if we have to balance, we have to balance Cl. So there should be 2 Cl over here. Now to balance the oxygen, we will write H2O over here. Okay. Now since there are 2 of them, we have to multiply water molecule with 2. And to balance the hydrogen, we will add 4 such proton over here. Now plus is the oxidation state of Cl in ClO forming Cl2, which is having 0 oxidation state. So 2 such electrons should be released. Okay. So this will be the balanced equation so far. Then we know we have to add OH minus ions on the both sides to proceed further. So we'll be doing it, but let us solve this one first. So over here we will write, to balance the oxygen, we will add 1 water molecule over here. Okay. So now that becomes 4. So to balance the number of protons, we will add, so here there is 2 and here there is, we can say here there are 3. So there are in total 5 such protons. Okay. Now what about the electrons? So over here we have a chromium in plus 3, that is going to plus 6. So now we will add 3 electrons on the, 3 electrons should be added on the right hand side over here. Okay. Because, so, okay. One more thing over here, electrons need to be added over here, not there. Okay, that is the correction, because it is getting reduced. Okay, sorry guys, correction over here, 2 electrons to be added over here. Okay, because this is getting reduced and not releasing electrons. Okay, so now we will be adding the OH minus ions. So over here, how many OH minus ions we will add? So let us do it here only, okay, instead of writing separately. So we will be adding over here, say, 5 OH minus ions, and here also we will be adding 5 OH minus ions. Okay. And now over here, how many we will add? We will add 4 OH minus ions, because there are 4 protons, and here also we will add 4 OH minus ions. Now the next step is always to add the OH and the H plus ions to get water. So now we will be writing these separately to have some clarity. Okay, and then we have Cl2 plus 2H2O and 4OH minus ions. Okay. So now we will take out the water molecules that are common. So here we have 1, here we have 5. So let us have one of these water molecules removed from the left hand side. That means it will be 4. And here we have 2 and here we have 4. So again we will remove this, and so we will write 2 over here. Now let us check if this is now balanced. Okay, so we have over here 8 oxygen and 8 hydrogen, 1 chromium. Here we have 1 chromium, 8 oxygen, 8 hydrogen. That is balanced. Okay, here we have 2 Cl, 2 Cl, 2 oxygen, 2 oxygen, that means 4. Okay, that is balanced. 4 hydrogen, balanced. And again the electrons are now balanced, taking care of the oxidation states of chromium in the first equation and chlorine in the next equation. So now let us call this to be as equation 1 and this to be as equation 2. Are the electrons balanced? No, they are not balanced. So again, just like the solution we had done before, we will multiply this one with 2 and that one with 3. Okay, so now, and then we will start adding these to get the final equation, and then we will simplify it further. So 2 into 5 is 10 OH minus 2 such chromium hydroxide, 2 such chromate, 8 such water molecules and 6 such electrons, 6 ClO minus, 6 water molecules, 6 such electrons. Let's go to that side now. 3 Cl2, 12 OH. And now we will be simplifying it further. So let us cancel certain things. 6 electrons gone. 10 OH, here is 12 OH, so we will remove OH from both sides. The excess amount will be written. Okay. This is. Now what about water molecules? Here we have 6 water molecules. Here we have 8. So cancelling them out, we will say 2 water molecules should be retained. And now let us write this over here. Okay. 6 ClO. Okay. So that should be the balanced equation over here, and that should be our answer. Okay. Voltaic cells. Now, the energy released in a spontaneous redox reaction can be used to perform electrical work. This task is now accomplished by using either a voltaic cell or a galvanic cell. It is a device in which the electron transfer takes place in the external pathway rather than directly between reactants when they are present in the same reaction vessel. So we are seeing one picture over here, the left hand side, in which you can see that copper sulfate is there, and we have put inside the copper sulfate solution a strip of zinc, and as we can see, with passage of time, the color of the copper sulfate solution fades out and becomes from deep blue to light blue. Now the color of the solution is due to the presence of Cu2 plus ions inside the solution. So what is happening with the passage of time? Zinc is going inside the solution as Zi2 plus, and the electrons being released over here are reducing the copper 2 plus to copper metal, And so that is why we can see some deposition of black or brown type of powder on the surface of the zinc sheet, and some are falling, at the bottom of the beaker. So the equation that we can write over here is zinc, that is metallic zinc, plus Cu2 plus ions equated arrow, giving us zinc 2 plus ions equated plus the copper metal. Okay. Now, so the electron that is being transferred from the zinc or lost from zinc, which is the over here the reductant, and Cu2 plus, which is the oxidant, this electron that is being directly transferred cannot be used to get some useful electrical work. But however, if we consider a separate type of an apparatus in which we are seeing there is a beaker in which there is we are having zinc nitrate inside the aqueous solution, and in that we are having a zinc plate being dipped inside it, and in another beaker we are having copper nitrate, and in which we are having a copper plate being dipped inside it. Now the two beakers are now connected by a U-shaped tube which is called as a salt bridge. Okay, we will be discussing in some detail what is the salt bridge, what is the role of it. Okay, now as in the picture we are seeing that we have assigned the zinc plate as minus and the copper plate as plus. So what exactly is happening, and why the electron is going from the zinc rod or sheet to the copper rod or sheet, okay, and what are the reactions taking place over here. So we'll be discussing this in some detail. Now let us move to the next slide. So we'll be switching between these two slides. The two solid metals that were connected by the external circuit, we call them as electrodes. Now the electrode at which the oxidation is taking place, we will be calling it as to the anode, and the electrode at which the reduction is taking place, we will be calling it as to be the cathode. Now each compartment of the voltaic cell is called the half cell. So let us just go back. So over here, this compartment having the zinc electrode and the solution having zinc nitrate inside it constitutes one half cell. Similarly, over here, this beaker having the copper nitrate solution and a copper electrode inside it is constituting another half cell. Now, as we can see, zinc is losing its electrons to the electrode and it will be going inside the solution as zinc 2 plus ions. Okay, so here we can say oxidation is taking place, and so this electrode will be having excess amount of negative charge, and that is why we are assigning it to be as the minus sign over here, and it is called the anode, rather zinc anode. Similarly, over here we can see that the copper ions from the solution are moving towards the copper plate, and over here the copper 2 plus ion are getting reduced by accepting electron from this electrode, which are being transferred from the zinc anode via this wire through the external circuit to this electrode, and so there is accumulation of copper ions over here, okay, as we can see in this enlarged picture, whereas there is corrosion of zinc from this electrode. So what will happen with the passage of time? As we can see, we have asked a question, why does zinc electrode lose mass and copper electrode gain mass? So we will see that there is loss of mass of zinc and there is a gain of mass for the copper electrode. So zinc anode, mass will be lost, copper anode, mass will be gained. So in terms of reactions, what we will say, in anode, oxidation reaction is taking place. So the half reaction will be written as zinc arrow, zinc 2 plus equated ions plus 2 electrons, okay. And for the cathode, the reduction half reaction will be copper plus 2 electrons, arrow giving metallic copper, okay. So this is the entire thing happening over here. Now, what is salt bridge and what is the function of the salt bridge? So salt bridge is basically a U-shaped tube, and This U-shaped tube is containing a very strong electrolyte such as potassium nitrate or ammonium nitrate or sodium nitrate, okay? And these ions will not be reacting either with the electrolyte present inside these two half cells or with the electrode present in these two half cells. But what is the function then of the electrolyte present within this gel? Okay, even before we discuss this, it is worthwhile to mention that this electrolyte is mixed with a gel or with a paste. The paste is called agar-agar, so that the electrolyte solution does not pour out from the U-tube into the solution. So what is the function of this electrolyte? So now let us think that the oxidation and reduction are proceeding in these two electrodes. Over here we are having the oxidation of zinc, and over here we are having the reduction of copper. So zinc ions are being introduced in the solution, that is producing excess amount of positively charged ions inside the solution. So to counterbalance that, we would need from an outside source excess amount of negative ions. So the negative ions are now going to move towards the anode. So we can say anions move towards the anode from the salt bridge. Okay, and similarly, since there is, as time passes, the copper ions are getting reduced and they are sticking to the copper electrode. So there is a deficiency of the copper ions in this solution, and we will say that to balance the charge inside this half cell, excess amount of cations will flow from the salt bridge inside the solution. So what the role of salt bridge is? To maintain the electrical neutrality of the electrolytic cell. Okay. Okay. Here we have an illustration, and it is about describing a voltaic cell. Illustration 6. The oxidation reduction reaction is spontaneous. The equation given to us is Cr2O72 minus plus 14H plus 6I minus, forming 2Cr3 plus 3I2 plus 7H2, and the sum reads as follows. A solution containing K2Cr2O7, that is potassium dichromate, and H2SO4 sulfuric acid is poured into one beaker, and a solution of Ki is poured into another beaker. A salt bridge is used to join the beakers. A metallic conductor that will not react with either solution, such as platinum foil. These are the platinum foils. Okay, is suspended in each solution, and the two conductors are connected with wires through a voltmeter or some other device to detect the electric current. The resulting voltaic cell generates an electric current, indicate the reaction occurring at anode and the reaction at cathode, the direction of electron migration, the direction of ion migration, and the signs of the electrode. Okay, so the reaction at cathode and reaction at anode, if you just go to the previous slide and we have a look at this equation, we can see already that potassium dichromate, the dichromate has chromium, and the chromium is in +6 oxidation state, whereas the oxidation state of iodide is -1, and chromium is going from +6 to +3 oxidation state. So there is a reduction over here happening. So whenever reduction happens, that means that half reaction will be belonging to the cathode. Okay. Now over here, iodide is getting oxidized to iodine solid. So this will be 0 because iodine at elemental state is 0. So wherever the oxidation takes place, that will be called as the anode. And we know the anode will be bearing the negative sign and the cathode will be having the positive side. Okay, what is positive sign? Now let us connect these two via a copper wire, and let us call this to be the voltmeter. Okay. So suppose these are now connected via some crocodile clip. Okay. So electron, let me first join the beakers with a salt bridge. Okay. So let us call this U-shaped tube. Okay. This U-shaped tube is the salt bridge containing a very strong electrolyte. Let us call that to be as NaNO3. So this would be the salt bridge to maintain the electrical neutrality. Okay. Now after connecting the salt bridge, electrons will start flowing from the anode. So this is the anode electrode, and we will be calling this one as the cathode. Okay. So over here, the direction of electron movement is going to be from the anode to the cathode. Okay. So over here, near this platinum electrode, okay, which is the anode, oxidation will take place. So we can say I minus will be losing 2 electrons. Okay, so 2I minus loses 2 electrons and forms I2, whereas as we know the electrons are coming to this electrode from the anode. So dichromate, that is Cr2O7 2 minus, okay, over here will be accepting 6 electrons, and that should form chromium 3 plus. Okay, so this is the reaction. So over here the anions will be moving towards the anode over here, okay, and the cathode will be reducing the dichromate ion to its other oxidation state, that is chromium 3 plus. Okay. So now, as the question had asked, reaction at cathode, we will say Cr2O72 minus plus 14H plus 6 electron, giving us 2 Cr3 plus ions plus 7H2O. That will be the balanced reaction occurring at the cathode, and it is the reduction reaction. Reaction at anode will be the oxidation, and over here 2I minus will be producing I2 and releasing 2 electrons. Okay, so we have covered all the topics over here. As the question had asked, indicate the reaction occurring at anode, reaction at cathode, direction of electron migration we have shown in the previous slide, the direction of migration of ion we have shown, and the signs of the electrodes also has been given. Now, we'll be learning about cell potential under standard conditions. So just like water flows spontaneously over a waterfall because of a potential difference between the top of the fall and the bottom, so also electrons flow through an external circuit from an anode of a voltaic cell to the cathode because of the difference in the potential energy. So potential energy of the electrons is higher in anode than in the cathode. So what is potential difference? Okay, it is the difference of potential energy per electrical charge between two electrodes and is measured in volts. So we can define 1 volt is the potential difference required to impart 1 joule of energy to a charge of 1 coulomb. So 1 volt can be shown by an equation, and that will be equal to 1 joule above 1 coulomb. Now the potential difference between the two electrodes of a voltaic cell is called the cell potential, and it is denoted as E suffix cell. Some more things about the cell potential. The cell potential of any voltaic cell is positive. We will be discussing spontaneous and non-spontaneous reactions. For any reaction to be spontaneous, E cell has to be positive. Okay? Otherwise, if it is negative, it is called non-spontaneous reaction. That means the reaction will not occur. The magnitude of the cell potential depends on certain factors, and that would be the reaction that occurs at the cathode and the anode, the concentration of the reactants and the products, and also the temperature. Standard reduction potentials, which are designated as E naught, is the voltage associated with the reaction at an electrode when all solutes are having 1 molar. Okay, this is important, and all gases are at 1 atm and the temperature is 25 degrees centigrade. The standard way of writing the standard reduction reactions are, we will place the oxidant, okay, over here within the parenthesis, then we will add the number of electrons, n is the number of electrons, put a reversible arrow, and we will produce the reduced form. Okay, so the oxidized species plus the electrons, then the product is the reduced form, and both have to be placed in parentheses, indicating that it means concentration of the, over here, the oxidized species and the concentration of the reduced species. Now, standard reduction potentials. Okay, so is it possible to measure the standard half reaction or the standard reduction potential of a half reaction directly? The answer is no. It has to be measured in reference to something. So what do? We can determine the standard reduction potential of other half reactions relative to a standard hydrogen electrode, which is also called as SHE or as a NHE, normal hydrogen electrode, or other reference electrodes. So we'll be discussing other reference electrodes in the coming slides. So the reference half reaction is the reduction of a proton to hydrogen gas under standard conditions, which is assigned a standard reduction potential of exactly 0 volt. Okay, so the reference electrode, we are assigning the voltage to be a 0 volt. Okay, this is a convention. Now, the reaction will be written in the following manner, that is 2H plus, the state should be mentioned, aqueous, the concentration should be mentioned, 1 molar, number of electrons required should be mentioned, that is 2 electrons, an arrow should be given, and then we will write H2, which is the product, and over here also the state should be mentioned, that is a gas, and it is having the pressure 1 atm, and the standard reduction potential or E naught red is going to be equal to 0. So again, a few points on the standard hydrogen electrode now. So SHE will be consisting of a platinum wire connected to a piece of platinum foil covered with finely divided platinum that serves as an inert surface for the reaction to occur. The SHE allows the platinum to come in contact with both the 1 molar H plus and the stream of hydrogen gas. Okay, so the platinum black is the surface at which the reduction of the proton is taking place to hydrogen gas. The reverse can also happen, that this H2 can get oxidized to 2H plus, releasing 2 electrons. Okay. So one more thing, that the standard hydrogen electrode can operate both as a cathode or as a anode depending on the nature of the other electrode or the half cell to which it is connected. Okay, so that has to be understood. So that means it is a reversible electrode. Okay, so here we have a nice picture showing the standard hydrogen electrode, and as you could see, these are concentric tubes. This is the beaker containing 1 molar of H plus ion concentration, and the gas is driven through this pinhole over here, which enters the tube. Okay, and then through this fine orifice, we can see it is coming in contact with the platinum black. Okay, and that is the platinum wire. Okay, now there is an outlet for the gas to be released. So proton and H2 are now in contact with the platinum black for the reaction to occur, and as we could see in an enlarged picture, on the surface of the platinum electrode, the half reaction that is occurring is 2H plus aqueous plus 2 electron reversible arrow, giving you H2. Now if you want to write this half reaction in this format, there is a method I am going to discuss that. What is the meaning of these? So first of all, the left hand side would be indicating the reactant and the right hand side will be indicating the product. Okay, and both of them are separated by a vertical line, which is this one over here. Now the vertical line indicates the phase boundary, which means proton, which is in aqueous medium having a concentration of 1 molar, is in a different phase than the H2, which is a gas and having a pressure of 1 atm. Now bringing these two things together is another phase boundary over which this reaction is occurring, and that is the platinum electrode, which is obviously a solid. So the physical states have to be mentioned, and the phase boundaries or substances existing in different phases has to be separated by a phase boundary using a vertical line. So this is how we write the half cell equation. Now here we have other reference electrodes, and what they are: silver chloride electrode, the saturated calomel electrode, or also known as the SE, or the glass electrode, which is commonly used to measure the pH, and we can also function as ion selective electrodes, which depend on the concentration of the single ionic species inside the solution. Now differences in potential between the SHE, this is an important point, okay, and other reference electrodes must be included while calculating the E0 values. That means SHE is having 0 voltage, but these 3 electrodes that you are seeing over here, they are not having 0 voltage. They will be having some other voltage. So those values have to be adjusted while we are calculating the E0 values for other half reactions that are occurring when these two electrodes are connected, okay, in an electrochemical cell. Now here are the pictures indicating how these electrodes are constructed, okay, what materials are present over there. So one can have a close look at these pictures to have an understanding what things are inside a silver chloride electrode or in a calomel electrode. Calomel means Hg2Cl2, which is a precipitate, okay. Now let us consider the reaction Zn S, that means metallic zinc, and the reaction is occurring between this and the two protons, leads to the release of Zn2 plus and formation of H2. So when these two things are connected and we are measuring the cell potential under standard conditions, the cell potential that we will be getting is going to be 0.76. Now by using this standard cell potential, that is E naught cell equal to 0.76 volt, and as we know the defined standard potential for H plus is E naught red equal to 0 volt, and using the equation one can calculate the half cell potential for Zn2 plus going to Zn. Okay. So using a reference electrode, I can know the half cell potential of the other electrode. Okay. So how do we do that? We use an equation for that, and that is E naught cell equal to E naught red cathode minus E naught red anode. Okay. So E naught cell is 0.76, 0 volt for the SHE, and as we can see minus E naught red anode, and once we do the math, we will be getting that the standard reduction potential for Zn2 plus going to Zn will be having the value minus 0.76 volt. Now, as we have measured the standard reduction potential for zinc, the standard reduction potentials of other half reactions can be determined in a fashion analogous to the way we have done in the case of zinc 2 plus going to zinc half reaction. Now, the standard reduction potentials, often called half cell potentials, can be combined to calculate E naught cell values for a large variety of voltaic cells. Okay. Now, here is an interesting thing, because electrical potential measures potential energy per electrical charge. Standard reduction potential are intensive properties. So the question is, by changing the stoichiometric coefficient in a half reaction, does it affect the value, or the question is, does it affect the value of the standard reduction potential? Okay. The answer is given, it will not. Okay. So that means that for this reaction, the value is this, and this is basically showing 1 mole of zinc being reduced by 2 moles of electron, giving you zinc, 1 mole metallic zinc. Okay. So this is 1 mole of zinc 2 plus ion. Okay. Reduced by 2 moles of electron, giving you 1 mole of zinc. Now, in case of that, if you take 10 moles of zinc 2 plus ion, 20 moles of electron, and produce 10 moles of zinc, will the standard reduction potential value change? No. It will remain the same, because it is an intensive property. Now, over here, calculating E naught red from E naught cell, illustration 7, for the zinc dash Cu voltaic cell, equation given to us is zinc solid plus copper 2 plus aqueous, 1 molar going to zinc 2 plus aqueous, 1 molar plus Cu solid. The E naught cell over there is 1.1 volt. Given the standard reduction potential of zinc 2 plus to zinc is minus 0.76, calculate the E naught red for the reduction of Cu2 plus to Cu. Okay. So we have already studied the equation. Okay, and that is E naught cell equals E naught red cathode minus E naught red anode. Anode means oxidation. So here zinc is oxidized to zinc 2 plus, so that will be the anode, and copper 2 plus getting reduced to copper, so that will be the cathode. So we will then write E naught red cathode is E naught cell minus no, it will be plus E naught red anode, okay, or we can now write E naught red Cu2 plus Cu. This is having the value 1.1 minus, we will write 0.76, okay, volt, and that should be 0.34 volt. Okay, so this is how we will be solving these problems.